Okay, thank you very much. And I would like to thank the organizers, of course, for the kind invitation to come to this conference. I'm looking very much forward to this week. I'd like to show you experiments which we do at ETH Zurich, in which we combine a Bose-Einstein condensate, so a quantum gas, with a high-finesse optical cavity. And this arrangement gives rise to long-range interactions between those particles, and this is my artistic view on what goes on. Two atoms here are interacting with each other over long distance via the exchange of photons, which are stored inside this cavity. Okay, when I read the advertisement for this conference, I was excited because it says exploring non-equilibrium long-range quantum matter, and that's exactly what we are doing. And in this spirit, I would like to first introduce you to our types of long-range interactions, and then give you two examples where this non-equilibrium behavior actually becomes very important. Okay, long-range interactions in quantum systems, and sorry Guido, I will say in quantum gases at the moment, rely usually only on dipole-dipole interactions. So you need somehow to create dipoles which then can interact with each other over long range. This can be done with strong magnetic dipole moments, heteronuclear molecules, or you induce a Rydberg atom, and then you have also an induced electric dipole moment. Our type of long-range interactions also rely on these dipole-dipole interactions, but they look a bit different. And this idea goes back, I would say, to a paper from Duncan O'Dell from 2003, who said, well, let's imagine you have a quantum gas and you illuminate it with light, far off resonant from the atomic transition. Then this light will induce dipoles in your gas, and those dipoles should be able to interact with each other over long range. So that was the idea, and now, well, this has not been really implemented, and there's a caveat here, because if you think of the microscopic picture, what you want is that a first atom is taking a photon from this laser, scatters it off in space, and then a second atom is capturing this atom and scatters it again. Then those two atoms would have interacted. However, the probability that this process can take place is very small if you plug in numbers for a dilute quantum gas. So we can enhance this process strongly by adding a cavity. So then our photon doesn't get just lost, but is recycled within this cavity. So that's our schematics. We put a Bose-Einstein condensate of rubidium-87 atoms into our high-finesse optical cavity, illuminate the atoms from the side with a standing wave transverse pump laser field, which is far off resonant from the electronic transition of the atoms, such that the atoms just act as scatterers. At the same time, we put a cavity resonance close by to the frequency of this laser field, such that photons are preferentially scattering into the cavity mode. Now, with respect to the free space case, you see that the scattering goes into a well-defined cavity mode, and the light field, the scattered field, is enhanced by the cavity finesse, which is order of 10 to the 5 in our system. So this makes what boosts now this interaction. The microscopic process stays the same. We are scattering photons from the pump into the cavity and back into the pump. Now, using a Bose-Einstein condensate is nice in this respect because you have now the well-defined momentum states. So if you think of the scattering process, then you will impart momentum onto those atoms, so they should actually appear as satellite peaks in your time-of-flight distribution. You can also describe this now in terms of those operators, and you see that we are annihilating two particles from the BEC and then creating two particles in different momentum modes, and those particles should be correlated. So that's behind our long-range interactions, is the creation and annihilation of correlated pairs. You could take a different description and say I integrate out the light field, and then I can describe the system as having an interaction potential, which is written here. So it inherits the standing wave character of the pump and of the cavity. This is giving rise to a checkerboard order, which is favored by this interaction. We can change the strength of the interaction by changing the power of the light shining onto the atoms and the inverse detuning between pump and cavity mode. That's not all. The system is an open system, so photons can eventually leak out of the resonator, which gives us also real-time access to the dynamics. I need to tell you about the single particle Hamiltonian. That's the full thing. I will only mention two terms here which are important for what I would like to show you. One is the kinetic energy. So this is the energy it takes to curve our wave function if the atoms should now acquire a density modulation. And then you have here this interaction potential, which I explained to you already, comes from the interaction between atoms and light. Okay, now we have a competition between those two energy scales, and this gives rise then to a quantum phase transition. So when the kinetic energy cost of bending your wave function is overcome by the gain in potential energy from this interaction potential, then the system undergoes a phase transition from a normal state without any density ordering of the atoms to a superradiant or self-ordered state where the atoms acquire this checkerboard density order. Then they sit on this checkerboard, and this is like forming Bragg planes at which photons can be efficiently scattered into the cavity. So that's our phase transition. If you would take a cut along the pump, you would find here a lambda periodic single well lattice in which the atoms form. Okay, this is a top view of our experiment. You see actually two cavities, but for the talk here, only one of those is important. And we have an auxiliary mirror, so if we shine a light here, you should think of a self-ordered state which looks a bit like this. This is our phase diagram. I plot you in color scale how many photons we count getting out of the cavity. So this is corresponding to the field inside the cavity. Whenever we find photons inside, the system is in the self-ordered state. That's shown as a function of the pump power and this detuning. So these were the two terms which are influencing the long-range interaction strength. We can not only look at the light field, we can also look at the atoms. So take a time of flight image, an absorption image after ballistic expansion, we find a pure Bose-Einstein condensate for a low or in this normal phase, and then in the self-ordered state we find this additional momentum peaks which correspond to the process of scattering those photons into the resonator and back. So this is the Fourier transform of a checkerboard density order. Okay. Now, this was my intro to our long-range interactions, and I now come to the parts which I actually would like to present to you. It's two things. One is a dynamical self-organization. So this is now leading to the concept of pumping. It's a geometric pump in the system which we induce. And the second part is that we wanted to have a closer look at this creation of those correlated pairs of atoms. In order to understand what goes on for this pumping, I need to introduce two more concepts to you. One is self-organization in repulsive fields, and the other one is an imbalanced pumping situation. Okay, so what I've shown to you so far, the light field was red detuned with respect to the atomic resonance. So atoms were sucked into the regions of high intensities, and then you can imagine that they easily scatter the light. But now imagine what happens if you put the atoms into a blue detuned field. So now the atoms will be pushed into the dark, and you can wonder whether at all this self-organization process can take place, and the atoms should then scatter photons into a resonator. A bit counterintuitively, this can happen. So what happens is that the atoms will move actually to the regions of highest intensity of this blue detuned light field. Then they scatter photons into the cavity. However, because you're sitting on the blue side of a transition, those photons get, or this field gets, an additional pi phase shift. So then we have the destructive interference of the cavity field with the pump field at the location of the atoms. So they are able to shovel their own hole in this potential landscape, and by this still self-order also in a repulsive field due to this destructive interference. Here's a comparison of repulsive and attractive interactions. So this is this attractive case, delta A, that's the detuning with respect to the atom, is smaller 0, phase diagram, time of flight image, and this cut along the pump I've shown to you already. This is what we would expect how the real space structure looks like, this checkerboard lattice the atoms form. For the blue detuned case, the phase diagram looks different. Well, it's blue because we are blue detuned, but most important, you see that this phase ends, the self-ordered phase ends at a certain critical pump power. So this is when this destructive interference cannot be overcome anymore, and the pump field is too strong for this system to self-order. If you take a time of flight image, it looks different. So now you see that only those two peaks are occupied. This corresponds to a stripe pattern and not anymore a checkerboard pattern which the atoms form in space. So it's a different kind of crystal, and if you take a cut along the pump, you would find that this modulation is now again lambda periodic, but it's a lambda periodic double well structure which forms. Okay, that was one ingredient. The other ingredient I wanted to show to you is the imbalance drive. So what I've shown you so far were experiments where we had same power from left and from right side, which means we have a perfect standing wave which the atoms experience. Now, we send more light from this side than from that side, which is characterized here by this 1 minus epsilon, to running wave with different powers. And you can imagine that then whatever is balanced gives rise to a perfect standing wave, but then, well, the excess light from one direction is the running wave component, and this will also put light into the regions which were originally dark. Accordingly, if you take now our phase diagram, you see that we find this characteristic phase of the repulsive self-ordering, but then where we had actually a normal phase, now we see the appearance of a new phase, which is visible again as photons leaking out of the cavity. So taking time-of-flight images, this was the stripe pattern, and now we take a time-of-flight image at this location, and what we observe is that we again find a checkerboard, although we are now using these repulsive light fields. We can understand this if we look at the single particle Hamiltonian. This is what I've shown to you so far, well, with the addition of this epsilon factor in front here. And most important, you find the cosine times the cosine of pump and cavity. So this is this checkerboard structure, which leads then to the formation of stripes. But now, since we have a running wave, and the running wave can be described as a sum of cosine and sine, you see that there's also a term with a sine of the pump appearing here. This flips the potential and gives rise then to this lambda periodic single wells. So this is what gives rise to the additional self-ordered phase here. Important is also to note that the stripes are coupling to the real quadrature of the cavity field, while the checkerboard couples to the imaginary quadrature of the cavity field. So since we have this real-time access to our atoms via the light field leaking out of the cavity, we decide to put a heterodyne detector which measures amplitude and phase of the cavity field. And if we do so, we can distinguish the real and imaginary quadrature of this cavity field, and indeed find that there's a pi/2 phase jump in between those two phases if we analyze here the phase of the light field. Good, so we drove a phase transition from one crystalline structure, the stripes, to the other one, the checkerboard, and observed what happens as a function of time. So that's shown here. On this plot, you see the phase, or kind of this measurement here now as a scalar value. You see how the phase changes as a function of time. And on the top plot, I show you, or I will show you the same data on a polar plot where I have also the radial component here, which gives you the amplitude of the light field. So if we run the experiment in real time, we observe that at this transition point here, we find a jump in the phase going by pi/2. There's some excess energy which is dampened out in the system at this first order structural phase transition, and then it settles to the new value. And very important, you see that there's never zero field inside the cavity, so there's always a lattice, there's always a structure of the atoms present. If you think what happens in real space, we have those stripes which deform into a checkerboard, and at the same time, indicated here by this Brinell zone, you see that the center of mass of your wave function is shifted by λ/4. So this gives rise then to this additional phase shift because your full scattering structure was displaced in space. Good, so what I've shown to you so far is all relying on coherent processes. And you can ask the question, well, at which point does dissipation become important? Good, so being coherent meant for us that this delta C, this detuning, this is the energy scale of the photons, which was much larger than the dissipation rate of the cavity. But we can go to the dissipative regime where they are similar. Repeating the experiment at this detuning, we find that, well, the phase diagram shows the same macroscopic phases, but it looks much more noisy. Indeed, this is not noise, this is interesting physics. Because if you take a cut along one detuning line here, you see that this phase is evolving monotonically in a step-like fashion from 0 to 7.5 pi. You also see that the postdoc who was taking this data, David Drion, is actually an Italian. So this is the phase of the cavity field. I can plot it again as a polar plot. And then you see here, that's the real and the imaginary quadrature of the light field, that this state is wrapping here around the origin. There's always a lattice on for the atoms. That's interesting, because now you can ask, how is the potential looking which the atoms acquire, or which the atoms feel, the self-consistent potential? You can write it down and decompose it into a short lambda over 2 periodic part and a long lambda periodic part, and this long periodic part is shifting as a function of this phase of the cavity field which we observed. So here's an animation of this potential, and you see that something moves in space. This was the moment where we realized what we have here is something which you might know as a topological pump, so the Thouless pump. It's a proposal from Matthias Treuer how to implement a Thouless pump in cold atoms. You take a short period and a long period lattice and you slide the two with respect to each other. This had been done in 2016 by the groups of Bloch and Takahashi, and you see that the effective potential which they used are exactly, well, our lambda periodic single or lambda periodic double well structures. And in their case, they had to encircle here a singularity in their parameter space, and we do something very similar. Our system is encircling here this singularity of zero field inside the cavity. Now, with this interpretation I've given to you of the different structures, stripe and checkerboard, each time when we go from one quadrature of the cavity field to the other, the system is moving by lambda over 4. That's our naive expectation. So we set up an in situ imaging and looked for the center of mass of this wave function, and indeed we find that this center is displaced as a function of the number of phase windings. Okay, so it looks like we have a DC current in the system, and it follows an AC perturbation. That's something you might know as a geometrical or an adiabatic pump, and one of the first ones was Archimedes' screw. So you need somebody who's turning this handle, so you have a time periodic Hamiltonian. But that was not the case in our system. We apply a DC field, and still the system shows this dynamics. So the resolution to this riddle is that our Hamiltonian is actually a non-Hermitian Hamiltonian, because we have to add here the cavity dissipation. So it's this phase shift acquired by cavity dissipation which gives rise then to an evolution in space and to this adiabatic pumping. Good. So this was one story I wanted to tell you, and I come to the other one. Going back to what I've shown to you at the very beginning, I told you that these long-range interactions are, well, in essence, based on the formation of these correlated pairs when you scatter a photon from the pump into the cavity and back into the pump. Then they were correlated in momentum space. Now, we set out to investigate this more closely, and I would like to show an experiment where we are able to single out these pairs, and we do it in a way that we actually find pairs of atoms which are correlated at the same time in their spin and their momentum degrees of freedom. It's a different setup, but the experimental tools are more or less the same. We have a standing wave cavity and we have a pump field from the side. Now this pump field is a running wave component only, so there's no standing wave involved anymore. Instead of looking over milliseconds or even seconds, we are using a very fast experimental scheme here, just tens of microseconds. And this light field is tuned to the tune-out wavelength of rubidium. So tune-out wavelength means that we tune it right in between the D1 and the D2 line, such that there's no scalar polarizability of the atoms left. So there's no potential which the atoms feel, no scalar potential. However, there's still the vector polarizability of the atoms. So if they scatter a photon, then they will actually change their spin degree of freedom, their Siemens substate. This is why we prepare now our atoms in the MF equals 0 state of rubidium-87 F equals 1 hyperfine manifold. So in this manifold, you have 3 Siemens substates, -1, 0, and +1, and we prepare all the atoms in the MF equals 0 state. And now, when they scatter a photon, it has to be scattered by changing a spin into plus or minus 1. Okay, so now we do the experiment. We shine our short pulse, and then we look in time of flight at our atoms. In addition to doing this time of flight, we are also doing a Stern-Gerlach experiment, such that we can resolve not only momenta, but also the spin state of the atoms. That's what we see. Most of the atoms are still in this MF equals 0 state where we prepared them. And you see that they are still at 0 momentum, which is the center of this picture. Then if you look at the segment where we record the MF equals +1 atoms, we find that, well, we find now atoms in this Siemens state, and they have a positive momentum acquired and also 1 momentum along the cavity direction. Similarly, for the MF equals -1 atoms, well, they are now pushed downwards, so they got a negative momentum. What I would like to convince you of is that these atoms here are correlated. And what we believe is that they're in very strong similarity to what you know from nonlinear photonics, where you can create entangled pairs of photons by shooting a laser field, a strong laser field, onto a nonlinear crystal, and then you get your single and idler photons, which are then correlated in their polarization degrees of freedom. So this parametric amplifier has a characteristicum that this number of pairs of photons which come out, it should increase superlinearly as a function of the pump power, and that's something I would like to show you that we also observe. Okay, we have an understanding, we have a microscopic understanding of the process. And it's the following here. We take an atom in this MF equals 0 state and shine our laser onto it. If it scatters a photon, it has to be spin flipped into another Siemens substate, which is here split by the Siemens splitting. Now we can tune our cavity to be on resonance with this process, and it's very likely to happen because then this photon is supported by the cavity mode. What will happen most likely then is that we lose this photon out of the cavity because it was so happy inside the cavity. We can do something else. We can detune this cavity away from this resonance condition. So now the process still can happen, but it's more likely that the photon will be reabsorbed by another atom and pulled out again out of the cavity. So this is what we believe what happens here. The photon is scattered into the cavity at the first atom. Now a second atom will re-scatter it into the pump. So the photon only virtually excites the cavity mode. And due to angular momentum and energy conservation, the second atom has to be actually scattered into the other spin manifold of rubidium. So this produces then a pair of atoms which are in the +1 and the -1 state. And if you now think of the involved momenta, you also understand why one component is pushed upwards and the other one is pushed downwards. So the first process here taking place is absorption of the photon. So this gives you a momentum in the positive direction. The second process is emission into the pump, which gives you a negative momentum for the atoms. Okay, so now we can count our atoms in this and in that state, and we call the sum of the two, well, divided by 2, is the number of pairs which we are recording. And you see that this pair number depends in this characteristic superlinear fashion on the population of our pump mode. Pump mode being here the size of the original Bose-Einstein condensate in the MF equals 0 state. So this looks like a parametric amplifier. Of course, it's interesting then to ask whether these atoms are correlated, whether they are squeezed, whether there's entanglement. Well, that's hard to access, but at least the correlations we could check. So you see here that we repeat this experiment many times, and each time, under the same conditions, we are measuring the number of pairs, and we see this pair number to fluctuate heavily. It's a bit worrisome at the beginning, but then we plotted them as a histogram. So you see here the number of pairs on the horizontal axis, and this is the frequency at which we observe this certain realization. So we can have a nice distribution here which has a mean value and has a variance, and the two coincide, which tells you this is a Bose-Einstein distribution. And that's something very typical if you have fluctuations, if you have quantum fluctuations seeding a process. So you need to think of these modes into which the atoms are scattered as empty modes, and that you need a quantum fluctuation or some fluctuation to actually seed this process. And since this is a fluctuation, also the number of pairs which are produced will fluctuate heavily. Indeed, we applied this thought and made our own truncated Wigner simulations. And you see, putting zero seed atoms into those modes, or having a seed compatible with those quantum fluctuations, we indeed find a distribution which looks very similar to what we observe in the experiment. That's different if we add now a single pair of atoms into this mode into which the atoms should be scattered, or even 5 pairs of atoms, because then you see that this distribution changes heavily and looks completely different. So this ensures us that this process is most likely due to quantum fluctuations. Okay. Well, I gave you this picture of first stretching an atom into the -1 or the +1, and then the other one into the -1 state. You could also ask if it's possible to do it the other way around. Yes, it is. So there's a second scattering channel here, and you see that it sits at a different Zeeman energy. So by tuning a magnetic field, we can make this process being important or not important, and then we can tweak our cavity detuning here to favor both channels or only one of those channels. So we did the experiment also with 2 channels. So here's again the repetition. That's a single channel, but we can now count the atoms also in this segment here, and then we find mean of 0 atoms which have been scattered here. But if we use this 2-channel configuration, we find again a Bose-Einstein distribution. That's a correlation map. So I correlate here the momentum state in a certain spin state with this opposite momentum in the opposite spin state, and we find 1 correlation peak here, while for 2 channels we find obviously 2 correlation peaks. Why is this a good resource? Why is it important? Well, you can think of those atoms, if they are really in a squeezed state or an entangled state, as an excellent resource for an interferometer. So we are still suffering from counting those atoms to the single atom level because we don't have the detection efficiency. We are working on this. But we can dream of it and dream of using it as an active interferometer. So it's an atom interferometer which doesn't have a passive beam splitter here, but has an active beam splitter. So this active beam splitter is this parametric amplifier. At the entry port of your interferometer, you produce a squeezed or entangled pair of particles, and then you inverse this process and recombine those 2 beams if you want again, and this should give you a sensitivity which is much better than what is allowed classically. Okay, well, we are still dreaming of this, but we can ask for coherence, because if you build such an interferometer, you want it to be actually coherent. So the question is, what's the coherence time of our system? That's shown here. Instead of having a very short pulse, we now vary the length of this laser pulse. And now we should have those processes where we create pairs of atoms, but then doing this for a longer time, we should also annihilate those pairs of atoms. So it should be a coherent process of creation and annihilation, like a Rabi oscillation. That's indeed what we observe here. So we see that the system evolves coherently over, well, up to 150 microseconds, we are saying. Well, what you see is green is the MF equals 0 state, so our initial cloud. Blue and red is plus and minus 1. And you see that blue dominates. And this is exactly what happens, what I told you, if we are not far enough detuned, then sometimes the photon is scattered to the cavity and then leaves the cavity and leaves behind a single atom. So this leads to an imbalance in this distribution here. That's not so good if you want to build an interferometer, but we have a knob to tune this. And this knob is the detuning between the cavity resonance here and the scattering channel. So you see here how going further and further detuned, we can suppress this process to be actually negligible. On the same slide, you see, well, in gray, you see this population imbalance. These are the gray data points. And I overlay this here with the number of photons which leak out of the cavity. So you see that they follow the same trend here, and this tells us that it's really this dissipative process which gives rise to this imbalance in our pairs. Okay, with this I'm at the end, and I would like to introduce you the people who did this experiment. It's two teams. One was this pumping scheme here, and the other one were those correlated pairs. And I would like to thank you for your attention.
Thank you, Tobias, for the very nice talk. Questions? Please.
So thank you very much. I have two. So when you're off resonance in the first story, does your transition dipole matrix element, what transition are you pumping to get the transition dipole if it's off resonant? You said that you started the story talking about these transition dipoles you can excite off resonance. What is the transition of that dipole?
It's the usual dipole which you know from
classical dipole.
Yes. So it's just you drive your atom. You can think of it as the electron and the nucleus, and you drive it presently, and that was giving rise to this dipole moment.
So like a Hertzian dipole, some type of oscillating dipole.
Yes. So it's the same process which we like to use to form dipole traps. So we shine a laser tweezer, and this will actually trap the atoms because you excite a dipole inside the atoms, which is then interacting with the exciting field.
Okay. All right. And then when you talk about the superradiant phase transition, can you see this in the weak excitation regime, or you have to drive it extremely nonlinearly into the full excitation manifold?
I know. So what I didn't talk about, and which would have been nice to talk about after Jose's talk, was we actually also analyzed the system before its phase transition. So weakly driven only, and then we have access to the critical fluctuations. So also in that system, we measured the critical fluctuations at the phase transition. It's since it's an open system, you expect that it behaves like a thermal system. Mm-hmm. So exponents of 1, mean field exponents of 1. What we observe is consistent with 1, while the closed system would tell you it's 0.5. Mm.
Thank you.
On the first part of your talk, maybe a very basic question. So you called it a topological pump. What is topological about it? Is there a topological invariant that is increased during?
I called it topological pump. I didn't call it. I called it an adiabatic pump. So where it relates to is SSH model and characteristics. And if you think of the experiments done in the groups of Bloch and Takahashi, they did not use just a Bose-Einstein condensate, but they used actually either fermions or a strongly interacting Bose gas, so in the 3D lattice. So this gives then rise to quantized transport in the system, which we don't observe here.
Okay, so it is similar, but you don't have a topological interpretation in your case. Is that correct, or?
Well, we're looking for it. Let's say it like this.
Okay.
I'm happy to discuss it.
Okay, thank
you. I had a question about the first part of the talk where you mentioned driving this first order phase transition from one crystalline phase to the other. Do you see this like nucleation thing happening, like, you know, the standard dynamics of first order phase transition, or is it fully coherent, more Landau-Zener? And
so you're asking for nucleation.
I'm just asking how you should think of that dynamics of that, right?
Yes, so what I would like to say is that the interactions in the system, which I've shown to you, are mediated by the cavity. The cavity is a single mode cavity, which means this interaction is of global range. So there's no notion of space in the system. It's an effectively zero-dimensional system. So I would not expect to find any nucleation processes here. It's a bit, well, it's a bit weird interaction, I have to admit. But it is an infinite range interaction. Also, if you think of correlation lengths, that concept doesn't make sense in the system. You can only think of correlation times. And that's what this critical exponent I was referring to is describing.
Thank you.
In the last part about the active atom interferometer, could you please explain again why this is a realization SU11?
Well, I'm not an expert in this. What I learned is that, or what you would like to see, it's a bit shown down here, is that you are creating your pairs, and then the system is in this, well, interesting entangled state. And now you have your interaction, which you want to measure, your perturbation, which you want to measure, acting onto the system. And since it behaves now very non-linearly, it will pick up a certain phase or one of those components. Then you need to do a time reversal, that's this step here. And at this point, the system actually tries to go back, tries to annihilate the pairs again. But since you had this perturbation, it is not able to do so. And that's what we would like to measure at the end. The exact definitions, I can't tell you. So we picked it up here.
Thanks.
Yeah, actually, I also have a question related to that. So this time reversal process, does it involve basically pumping from the other direction, or how would it look like in this system actually? So, yeah.
We would like to do it by swapping a detuning in the system.
Like getting another process on resonance, basically. Yes. But what would happen if you kind of flip the direction of the pump? Would these kind of plus minus K peaks get soaked back into the 0 MF equals 0 peak, or is it more complicated?
No, probably it's fine. What I'm wondering is only if you need to fulfill a certain phase condition, because now once you have a second pump, you might add a phase reference, which is a bit dangerous.
Oh yeah. Mm-hmm.
But the process itself would invert. I agree.
Okay.
But
Tobias, can you elaborate a little bit more on the role of the non-emission part of the Hamiltonian in the first part of the talk? Mm-hmm. So you said that the non-emission part replaces the periodic driving in the standard picture of the adiabatic pump.
Yes, exactly. So in the standard picture, you have those two lattices, long and short, and you slide one with respect to the other. You do so by having your function generator, which you plug in there, and then it does the sliding. Now, if you think of the lattice which our atoms produce self-consistently, they're scattering photons into the cavity, and those photons will have, or this field has a phase which is dictated by the phase of the driving field. You can again think of small dipoles which are excited classically, and they scatter into the cavity, and that gives you a certain structure. Now, if you put the drive close by to the cavity resonance, then the cavity resonance, well, has its Lorentzian shape, but also has a dispersion. And if you now are close to the cavity resonance, you pick up an extra phase from the dispersion of the cavity. And that's this non-Hermitian part. So now you have your light being scattered into the cavity at, well, you would say at the phase of the pump, but then the cavity adds a certain phase shift, which means the phase inside the cavity is different than what is consistent with the formation of this atomic pattern. So the atoms have to adapt their shape they move a bit, but then also, again, the scattered light will have to move, and this sets you on this, what's an instability which is triggered here.
Okay. Any more questions? Yes, please. Okay, there are two. Let me start with, please, Nicola.
Since we seem to have a minute time, maybe I just can comment on the SU11 question we had before. So in this paper by Jurke, they show that in an active interferometer you can write each of the main processes in this interferometer as a generator of the corresponding group. So the different generators for the amplifier and so for the other steps. And in a regular, like passive interferometer, it's SU2 actions instead. So you end up with a sequence of actions of generators, which makes it a very rather convenient object to work with, and it has a nice group structure. So maybe that was in the direction of your question.
Thanks.
You have a last question?
So this effect with this like shifting lattice or whatever, does that happen for any dissipation rate? Like is that effect like really small if that dissipation is small, or does it or does it have to be like, is there like a critical dissipation where that behavior starts happening?
It's important. The strength of the dissipation is important, but it's important to enter the regime where delta C is similar to kappa. So that's always a scale which you can try to adapt. I showed you that we have two cavities. One happened to be worse than the other. No, one happened to be better than the other. And the worse one has the larger dissipation rate, and this one shows the nicer steps here. So it seems that the process becomes a bit more robust, but it happens in both cavities.
Okay, so if there are no other questions, let's thank Tobias again.